So for this problem, I'm going to use a different method of solving it. I'm going to be using a known versus unknown chart, which involves writing down the variables that are known, the variables that are unknown, and that allows you to pick a kinematic equation to choose, and it just makes solving all these problems 10 times easier. And I'll be solving an example problem as well. I'll be solving this question here. So this question here is asking for the minimum speed needed for the tennis ball to clear the net. So the tennis player is hitting a ball and it's going 15 meters across, slowly going down, and it needs to clear a net that's 0.9 meters high. This is the minimum, so it just needs to clear it. It can be touching it. So for the known versus unknown, let me just... This was just the example and the diagram, but now we'll move on to the working out. So we will use known information. We know, so what we know is, we know the initial y. So the initial y, which is just the height of the tennis player. So 2.5 meters. Right there. So 2.5 meters. We know the initial x, which is 0 meters. We know the final y, which is the height of the net, which is 0.9 meters. We know the final x position, which is 15 meters, because the distance between the net and the player was 15 meters. And then we have the acceleration in the x direction, which will be 0, as we are not working with air resistance. We have the acceleration in the y direction, which we will treat as negative 9.8 downwards. And we also know the initial y velocity, because gravity hasn't acted on the object yet, so therefore its velocity is going to be 0, because it's not going downwards or upwards. So v initial y equals 0. For our unknown, or what we want to solve, this is a multi-part question, so I'm just going to write down all the unknowns, and then I'll separate them into the multiple videos. So what we want to know in this video is the initial x velocity, the time, because we need to know the time to solve the initial x velocity. We will also want to know the initial final x velocity, but that's later, and the initial final y velocity, but that is also later in another part of the problem. So first things first, I'm going to identify which equation would allow me to solve t. If you remember, it will be the second kinematic equation, x equals x initial plus v initial times time plus 1/2 at squared, because it has t the most and it has most of the variables upon which we have. So we could transfix it and juxtapose it into the y version of the equation. So we will get y is equal to y initial plus velocity initial times time plus 1/2 at squared. So we have our final y, which was right here, so we have 0.9, is equal to the initial y, which we have right here, which is 2.5, so 2.5, plus the initial y velocity, which we worked out to be 0, because nothing's acting on it just yet. So that whole term will just cancel out to 0, so get rid of it. Plus 1/2 a is negative 9.8, because it's the acceleration in the y direction, times t squared. So working this out, you can subtract 2.5 from there, expand this. You'll end up with negative 1.6 equals negative 4.9 t squared. From this, we could divide by negative 1 on both sides. I'll fold this over so we can see. So we can divide by negative 1 on both sides, which will cancel out the negative that is acting out here, to get 1.6 equals 4.9 t squared. From here, we can divide 1.6 by 4.9 on both sides to isolate t squared. So let me put this into my calculator. and we get 1.6 divided by 4.9, which is this number here. And that's t squared. So to isolate t, we'll take the square root of it, and then I'll just enter it there. And we get this value here. So we have isolated time, and we have solved it to be equal to 0.571428571. Cool. Now that we have t, we can mark that off as an unknown, and we can just say we've solved it, because I'm not going to write out the whole entire decimal. Now we can use what we know here. We can use actually the exact same kinematic equation, but in terms of x, because now we have time. So our final x position was 15 meters. So we have 15 is equal to our initial y, which was 0 because we're starting at 0, 0, plus the initial t. That's what we want to solve for. This is the big number. 1/2 at squared. If you remember correctly, since we are working in the horizontal direction and there is no air resistance, because there is air resistance, but we're saying it's negligible and we're not factoring it in, that whole term is just going to cancel to 0. So that will just factor out, and this will be our final equation, and we will be left with 15 equals v initial times time. And I will divide 15 by our what we solve for t, and I have it right here. And you get this, 26.25000002. So the question says to round it to one decimal place, so we get 26.3. We need to add the units back in now because we're working with velocity, so meters per second equals v initial x. It's asking us for the since it's asking us for the minimum speed that it needs to hit the ball, that is only in the horizontal direction, as it won't be hitting it upwards, it's just hitting it across, as can be seen in the diagram. So therefore, we don't need to do any of what we did last episode to work out the total velocity. This will just be the answer to the question. The minimum speed that the tennis player needs to hit the ball with to just cross the net is 26.3 meters per second.